The topic of today's discussion is exponential map. Okay. In this discussion, we will discuss some interesting properties of exponential map. Okay. So for this, let us consider a power series. So first we consider a power series, and we check this power series. This power series is convergent for all z whose modulus is finite, right? Okay. So this power series gives us a function. So let us define a function f from complex plane to complex plane by this power series. Okay. Okay. So this definition is well defined because this power series is convergent for every finite z. Okay. And this function is denoted by this symbol, exponential. So exponential of z. Okay. So the first property we have observed is that what is the value of exponential of 0. So if we put z equal to 0 here, then we see that 1. What is the second property? The second property is very interesting. That is, this is a power series. Okay, this is a power series. So term by term differentiation is permissible. So we can derivative. So we differentiate exponential of z. So what is that? If we derivative it, so what we get? We get n equal to 1 to infinity in z to the power n minus 1 by factorial n. Okay. So after rewriting it, we can write it as, if we put n minus 1 equal to m, so we get m equal to 0 to infinity z to the power m by factorial m, right? Okay. So this is nothing but the power series of exponential function. Thus derivative of exponential function is same function. Okay. This is a very important property of exponential function. Okay. So we define the exponential function using the power series, and then we derive two properties, that is exponential of 0 equal to 1 and derivative of exponential function is itself, right? Now if we put z equal to 1, what we get? We get e. Okay. So this is a e means the transcendental number e. So that e is okay. Next we prove another important property of exponential function, that is what we prove. Next property is very important property. For any two complex number z1 and z2, we will prove that exponential of z1 multiplied by exponential of z2 is exponential of z1 plus z2. We will prove this theorem. Okay. So for that, before proving this, we will prove another result. Okay. So let us take any complex number. Okay, and we define a function from complex plane to complex plane by this. Okay. So this is a well defined function. Okay, and obviously this is a differentiable function, correct? So what is the derivative of this function? Derivative is derivative of exponential z is exponential z, and then derivative of this function is e to the power c minus z, and derivative of c minus z is minus, right? So this is 0, right? So, we see that G is everywhere differentiable function, that means G is analytic, G is analytic on C, and derivative of G is 0, and C is open and connected, correct. That means G is some constant, so that constant is C1, correct. Then what is the value of G of 0? G of 0 equal to, if I put 0 here, that is e to the power c, correct, and this is actually C1, correct. Thus, what we have established, Gz equal to G0 equal to C1, correct. Since G is constant, that means e to the power z, what is Gz? E to the power z multiplied by e to the power c minus z is same as e to the power c, correct. Okay. Now, if I take z1 equal to z and z2 equal to c minus z, then what we get? We get e to the power z1 into e to the power z2, these are the same as e to the power z1 plus z2, that is we wanted to prove. Okay. The next property is e to the power z into e to the power z equal to e to the power 2z, right. So, if we apply mathematical induction, then what we get? E to the power z to the power n is same as e to the power nz, where n is an natural number. This comes from principle of mathematical induction. Okay. The next property, so what is e to the power z into e to the power minus z? This is by property 4, e to the power z minus z, that is e to the power 0 and e to the power 0 is 1, so this is 1. So, e to the power z into e to the power minus z equal to 1. Okay. Since C is a field, so and the product of two complex number is 1, so e to the power z is obviously non-zero complex number, right. And since e to the power z is non-zero complex number, so e to the power minus z can be defined as 1 by e to the power z, right. So, now using 5 and 7, one can prove that e to the power z whole to the power m equal to e to the power mz, where m is an integer, correct. Next property, what is e to the power I into y? By this series expansion, we can write it as summation n0 to infinity iy whole to the power n by factorial n, right. So, now we take the even terms and odd terms separately, right. So, we can write it as, so this is actually series expansion of cos y and this is a series expansion of sin y. So, this is actually cos y plus I into sin y. Okay. So, if we assume the definition of exponential z by this power series, then we can prove that e to the power iy is cos y plus I into sin y. Okay. Then naturally we can write e to the power z as e to the power x plus I into iy. So, this is actually by 4 e to the power x into e to the power iy, and this is actually e to the power x into cos y plus I into sin y. Okay. So obviously e to the power z plus 2k pi I equal to, just to use this formula you can write is e to the power z, right. That means this is a periodic function with period 2k pi I. Okay. And another important property is what is the value of e to the power I pi, e to the power I pi. So if I, this is actually by 9, this is actually cos pi plus I into sin pi. So cos pi is -1, sin pi is 0, this is -1. That means e to the power I pi plus 1 equal to 0, and this formula is known as Euler's formula. Okay, this is a very famous formula. Okay, so we derive 12 properties of exponential function using the definition of exponential function as the power series expansion of this, right. Okay, thank you.